an effective fold for spaceflight is it has to be idiot-proof, essentially, right? It has to be simple and effective. You cannot have complicated mechanical machinery that will fail. The fewer points of failure, the better. And it has to be able to open up, essentially, without any possibility of failing. And it turns out that's something that origami is really, really good at. Obviously, the mirror fold has a lot of analogs in traditional designs, paper lanterns, and in cameras. Here's what a mirror fold actually looks like. If you go to Kyoto today, apparently, you can still get maps of Kyoto that are done in the mirror fold. So tourist maps. So you get it and you can just open it up. It looks really cool. The idea is it's essentially a tessellation, a mathematical tessellation. It requires you to do parallel folds in one direction and then zigzag folds in the other direction, so that you end up with a surface full of alternating mountain folds and valley folds. That way, when you apply force at the corners, it just compresses very easily. Let's see if I can actually get this to work. So, back. Okay, let's see if I can press this. Let's see what it looks like. So, this is an origami solar array prototype. No astronaut assembly required. Cool, huh? So in the compressed form, you can see how that can fit inside a rocket tube to be launched. And once in space, one application of force and it just unfolds. And it doesn't fail, it's not gonna get caught, it will actually work. This is a JPL experiment. This has actually been done. This particular one, I believe, was not launched, but a Japanese spacecraft recently did in fact launch a solar array that used the principles of origami to expand. So spaceflight. Turns out that origami is also shows up in the biological sciences. A lot of you have seen how dragonflies, when they go from nymph to their adult stage, they come out and they expand their wings. So one question that scientists have been struggling with for a long time is how does the wing fold up into that tiny little tube, and how does the dragonfly expand it out without breaking the wing or causing it to foul like a piece of cloth? It turns out that dragonfly wings are curled up in the nymph stage using essentially mirror folds. You can see that there are parallel lines, veins in the wing along the edge, and then there's a pattern of zigzag in the vertical side. There are very few right angles. So if you observe how the wing gets compressed and expanded out of the nymph stage, it's basically a natural version of mirror fold, and we never knew that until biologists figured out this application from origami. Similarly, tree leaves, when they're unfolding, turns out to use the same principle. Nature settled on the solution that origami artists discovered. Again, you do parallel folds in one direction, zigzags in the other, and so leaves do the same thing. Here is the pattern of embryonic turkey, the intestines of an embryonic turkey. Again, you see how the organs inside are again folded up in that same pattern. It's a very important development technique. Another place where you see origami shows up in modern science is metamaterials. Metamaterials are essentially materials whose properties are derived from repeating patterns at the microscopic scale. Tessellations, essentially. So here's one, a programmable metamaterial. So what you see there is a piece of material that's done using mirror fold. And what the person is doing is creating what are called pop-through defects by reversing the mountain and valley folds in certain specific places, he changes the properties of the material. The material now is not compressible anymore, right? Remember, traditionally a mirror, a fold surface will compress to a tiny space neatly if you just apply force, but by popping through a few places on that surface, he makes that part no longer compressible. So if you think about it, you can design a material that uses mirror folds at the microscopic scale. And so it normally can be compressible into a tiny space. But if you wanted to, you can programmatically introduce pop-through defects in specific places to make it hard and rigid and no longer compressible. So you can create a material that can go from soft to hard on the fly, essentially by programmatically changing a few places. That's a very powerful ability. I actually spoke with this researcher who was at Harvard, and he showed me a lot of interesting results. But right now they're working on cataloging and tracing through all the different characteristics you can obtain from material by creating pop-through defects in different patterns. And we want to catalog through all of this and be able to design essentially a material that you can reprogram and change on the fly by telling which particular folds to pop through. Here's more information on the mathematics of it. I have a list of references on my website, so you can look up the papers that discuss this. And they have many more fun movies showing exactly what happens to the material when you do pop-through patterns in certain ways. Okay, so now we're going to talk about geometry. So fundamentally, paper folding origami is a geometric exercise, right? It in fact is a very, very old technique of teaching. In fact, I was looking at a copy of Euclid's Elements published in 1570 that contained within it pop-up geometric figures inside the book. So clearly these took a huge amount of effort to produce, because after printing and binding the book, somebody had to go in there and actually paste these pop-up figures in there. But they are essentially paper versions of geometric figures like pyramids, the geometric solids, or mathematical proofs that you can hold and refold to be able to feel, to actually have a tangible model that teaches you how it works. The modern tradition of this comes in India. There's this book called Geometric Exercises in Paper Folding by T. Sundararajan, who we don't know who the person is, but this is an amazing book, an absolutely amazing book. So if you're a parent, you probably know the Montessori method of teaching, which is very much about manipulation, about learning through feeling things. One of the ways that Montessori method teaches geometry is by having children work with models, with creating building models, fitting them together, folding them. This is sort of like the early version of that approach, in which paper folding is the way used to teach children about geometric principles. So for example, in the introduction, the author says, it would be perfectly legitimate to require pupils to fold the diagrams on paper. This would give them neat and accurate figures and impress the truth of the propositions forcefully on their minds. What is now realized by the imagination and idealization of clumsy figures can be seen in the concrete. Okay, so this is seen as a teaching technique where by folding pieces of paper, you learn geometry in a way that you cannot otherwise learn by merely reasoning with figures on paper. Here is one way to use paper folding to prove to yourself the Pythagorean theorem. That's the a squared plus b squared plus c squared. The idea is this. So you take a piece of paper and you fold it using these creases. And what you end up with is the idea that here's a triangle, right? This is a square. And that one over there is b square. and that square over there is c squared. And you can easily see that the area of this thing is basically the sum of this thing, and cut the pieces out of here and you fit it up there. You take the yellow pieces and fit them into the blue spaces to prove to yourself that a squared plus b squared actually gives you c squared. And I love that, the fact that you can actually fold these figures, cut them out, and actually prove to yourself concretely that this is true. There's a certain sense in which you feel the truth of the proposition that you cannot through abstract reasoning alone. And here's another example which I would invite you to try yourself. There's a fallacious proof for why every triangle is isosceles. And you basically work through this, and if you're working through this on paper, it's very hard for you to see why the proof is false. But once you take a piece of paper and you try to actually fold the figures, you will see almost right away why it doesn't work, because the lines just can't fall within the triangle as described. But it's not something that you can see if you're just drawing figures on paper. You really feel it when you're trying to create the figures out of paper. The book even goes into a way for you to teach yourself conic sections using paper folding. So the idea is, we all know that a parabola is the set of points equidistant from a point known as the focus, and the line, which is known as the directrix. Okay, so this is the directrix, and that over there, that point S is the focus. You can see the parabola. So the book teaches you to take a set of points along the directrix and try to fold them to the point S. And then each time you fold, you mark the point where that fold occurs, which is a tangent to the parabola. And then you connect all of those points together and you get your parabola. You're literally using paper folding to recreate the idea of equidistance, okay? It's a very literal, very concrete way to get people that feel for how a parabola works, why it works, and why the set of points function the way they do. So now we come to the bigger point. A lot of modern mathematicians have been looking into origami and the kind of geometric figures you can construct using origami. And it turns out that there's a very interesting parallel between the kind of things you can do with origami versus the kind of things you can do with the classical Greek practice of compass and straight edge, right? So there are certain things you cannot do. We have proven that you cannot do using compass and straight edge. But it turns out they are actually possible using origami. One of them is the whole idea of trisecting an angle. Okay, this is a classical problem. How do you divide an angle into 3 equal pieces? That is not possible by compass and straight edge. Well, turns out there is a technique, a set of techniques you can follow in origami to achieve it. So now the question becomes, why? Why is it that, because originally when origami was first being studied, the assumption was that origami would be no more powerful than compass and straight edge. Whatever you can do with compass and straight edge, you can probably do with origami, but there shouldn't be anything you can do with origami that you cannot do with compass and straight edge. And here we have a specific example where that is not true. Well, the way it's not true turns out to rely on something called the Belloc fold, named after an Italian mathematician. It's the idea of taking 2 points, P1 and P2, and fold them so that simultaneously fall onto 2 lines at the same time. And that technique, which you see being applied over here, is the key to why the trisecting algorithm works. It's a Belloc fold. So what exactly is the Belloc fold? Well, it turns out earlier when I showed you how to create a parabola by folding a point onto a line, remember what I said? You're creating a tangent to a parabola when you're doing that fold of meeting one point specifically to a line. If you remember back to your high school algebra, solving a quadratic equation is essentially equivalent to finding that tangent line, okay? So this suggests that basically compass and straight edge techniques are solving quadratic equations. which is something that origami can do. But when you're folding 2 points onto 2 lines, you're essentially finding simultaneous tangents to 2 parabolas, okay? And if you remember back to your old geometry, this is not a proof, okay? This is not a proof, but this is very suggestive of the fact that origami, especially the Banach fold, is essentially equivalent to solving a cubic equation, not just a quadratic one. And that explains the additional power of origami as a geometric construction technique over compass and straight edge, because you can solve a higher order of equations. What this ultimately is, why this is interesting to me, is I love thinking about alternate science and alternate scientific history. So I keep on imagining, what if the classical Greeks, in addition to exploring problems about compass and straight edge construction, actually explored origami construction problems? And of course, we all know there's this period of time in Japan where monks in temples became obsessed with solving geometry problems. And we actually have still hundreds of years worth of geometry puzzles that the monks in temples produce. How wonderful would it be, if we can imagine this alternative history in which the monks or the classical Greeks, take whatever your pick is, decided to explore origami as an alternate geometric technique and form an entire geometry different from Euclidean geometry based on the potential possibilities of paper fold. It's the sort of thing that I, as a science fiction writer, get very obsessed with. But now here comes the important part, okay, which is why am I so interested in origami? I think there's a deep power and a lot of value in being able to manipulate things that are otherwise only ideas in the abstract. So remember what Rowe said, what is now realized by the imagination and idealization of clumsy figures can be seen in the concrete. There's something very different about your brain's processing power when you're able to hold something and work with it with your hands, when you're able to manipulate it. I think that actually is the power of a lot of science fiction and fantasy. The sort of fiction I write, which I describe as literalized metaphor fiction, is exactly like that. What I do is I take ideas that are otherwise very abstract and hard to visualize, and I make them into concrete figures that you can manipulate. So we can talk about a mother's love in some abstract way. We can talk about a mother's love as an animating principle behind everything she does. Or we can make that concrete, make that metaphor concrete by saying she literally breathes her love into a set of paper animals and make them come to life. Once these animals are living things in the reader's imagination, you can do things with these animals to explore the concept of love that you cannot do otherwise if they remain intangible, abstract concepts. So this is what I like about the sort of fiction I write. I try to make what is otherwise merely idealized and visualized through clumsy figures into concrete, manipulable, literalized metaphors that you can then put through its paces for readers to get a tangible feel for what it is that I'm trying to explore. Most of my fiction can be understood in that vein. Most of my fiction can be understood as the realization of the idea of basically manipulable geometry. So that's my little presentation, and thank you very much for your time. If you are interested in this sort of topic, you can definitely go to my website and download the list of resources, papers that I cite.